We're going to take a look at the notes for lesson 1-4. The first thing that you need to do is get out your term sheet for chapter 1. The 1-4 is going to be on polygons, so it's on the back side of the term sheet for chapter 1. You also probably want to get out your book and turn to page 54. Most of the terms that we're going to run through you can find on page 54, and if you miss something you can go back and take a look at it there. So polygons is what 1-4 is about. A polygon is a closed plane figure formed by connecting line segments from endpoint to endpoint. Common polygons that we know about already are triangles and squares and rectangles and pentagons and things like that. This list is on page 54 of your book. You will probably want to fill this in. We should already know three-sided figure, triangle. We should know quadrilateral. Rectangles and squares are quadrilaterals with special circumstances. In general, most people seem to have no problem identifying triangles and quadrilaterals. Pentagons, the large building that's in Washington, D.C. that houses the Defense Department. Hexagons is 6. Those ones people seem to remember. Octagons and decagons, there's 10 years in a decade. Coincidence? I think not. Heptagon is one that seems to be a little bit more difficult, so you probably want to pay attention to that one. Nonagon is 9. We don't really use the undecagon for 11, or dodecagon, which is one of my favorite words in mathematics, for 12. And one would assume then that a 13gon would be a tridecagon and quaddecagon and things like that, but that's not the case. At some point a mathematician said, this is ridiculous to have all these prefixes. Let's just go ahead and put in numbers in front of gon, which is the sided figure portion of what we're talking about. So polygon, poly means many, gon means sided figure, so many-sided figure. So once we get to, say if you had a 22-sided figure, you just write 22 gon. Or if you had a 14-sided figure, you write 14 gon. So you do need to know what all of these things are. Specifically 1 through 10, 12 comes up, and actually I remember 11 coming up as well. So you should commit those to memory, and most of them you probably already know. Again, hepta seems to be the one that students have a little bit of a problem with, and nana, but if those are the only two that you don't know, you should remember them fairly swiftly. Again, those are on page 54 of your book. If you didn't get them written in, that list is there provided for you. A diagonal, we'll work with a lot with diagonals throughout the entire course. A line segment that connects two non-consecutive vertices. Well, I guess we should probably go back and talk about consecutive and non-consecutive. Consecutive is right next to, here's A and E, and they are consecutive angles or consecutive vertices, and they're right next to one another. Notice that's what we connect to form the polygon. Consecutive sides are right next to each other. They form an angle on the polygon. So consecutive just means right next to. So when we go over and talk about diagonals and talk about connecting non-consecutive vertices, then we're going across. Obviously D and E are consecutive. You can't draw a diagonal when they're right next to each other, but we could draw one from D to F. I also could draw one from E to G. So this quadrilateral could have two diagonals drawn from vertex to vertex. There aren't any others. So the diagonals are going to be very important when we come to classifying our different types of polygons. Convex polygons, all the diagonals are inside the figure. If all the diagonals are inside the figure, you have a convex polygon. Here's some examples of them. Notice triangles actually don't have any polygons. There's no way I can draw to a non-consecutive vertice, but all triangles are considered convex polygons. Here's two quadrilaterals. This is a 1, 2, 3, 4, 5, 6. This is a hexagon, so we would call this a convex polygon. Every single diagonal that is drawn is on the interior of the figure. Concave polygon is the opposite of convex. Concave, notice it says at least one. You could have multiple, but you only need one. So here are two non-consecutive vertices. We draw the diagonal. It goes outside the figure. The black figure is the enclosed. That makes it concave automatically. I like to think of it as when we have a concave, we form a little bit of a cavity or a cave there, and that's what tells us we're concave. So here's one with two. Here's one with two. This is a funky figure. 1, 2, 3, 4, 5, 6, 7, 8. This is an octagon. Remember, often when we think of octagons, we automatically think of stop signs. That's not the case. It could be anything with 8 sides is going to be an octagon. This looks like an hourglass, but it's actually a hexagon, and this is a weird looking pentagon. So those are all concave. So we would call it concave, concave pentagon, concave hexagon, concave octagon. Next terms, equilateral. Equilateral. We often think of the term equilateral and we immediately assume it's an equilateral triangle. Any polygon can be equilateral. It just means that we have all sides are congruent in a polygon. So here's 3 sides congruent, 1, 2, 3, 4, 5. This is an equilateral pentagon. Here we have 1, 2, 3, 4. This is an equilateral quadrilateral, and some of you may already know that an equilateral quadrilateral is a rhombus. A rhombus, one of my favorite words in mathematics. 1, 2, 3, 4, 5, 6. This is an equilateral hexagon. This one fails because it only has 2 sides congruent. It's an isosceles triangle. This one fails because it has opposite sides congruent. It's a rectangle. This one is not a polygon. It's the letter Z, apparently. And this one fails because not all of them are the same. Equiangular. Equiangular. All angles are congruent. All angles are congruent. So here we have an equiangular triangle, which you may already know is an equilateral triangle. Actually, an equilateral triangle is both equilateral and equiangular. Equiangular quadrilateral, equiangular pentagon. This one fails because only 2 angles are the same. This one has something about sides, doesn't have anything to do with the angles. This one has no markings, and this one is a circle, which doesn't have any angles at all. So equiangular, all the angles are the same. Regular. Regular polygons always go to the bathroom at the same time every day. That was a joke. Regular polygons are both equilateral and equiangular. Now, we automatically know this one. We've known this one for a long time. We call that an equilateral triangle, but again, it's both. It's both equilateral and equiangular. So regular polygons will work a lot with regular polygons. It's whenever we say something's regular, we automatically know that all the angles are the same. A regular quadrilateral is actually a square. These would have to be 90. It's the only way it works. This is a regular pentagon. This would be the building in Washington, D.C. would be formed as a regular pentagon. You'll notice these are not regular. Sides are not all the same on this one. Only 2 angles are marked here. Sides are screwed up. Nothing's marked. This is equilateral, but it's not necessarily equiangular. We need markings. We must have markings. Congruent polygons have the same shape and same side. Corresponding matching sides and angles are congruent. It is very important that you understand that the order in which the letters are written directly corresponds to which ones have the same angle measure or which ones can include the same side. So if you look at angle C here and angle S, notice they're both marked with a single tick arc, and they're in the same position on our congruence statement. This is called a congruence statement. It tells us which of the vertices match up. So here I have A in second position and I in second position. So C matches with S, A matches with I, M matches with T, P matches with E. The angles match up. If you notice, MP has a triple tick, and TE has a triple tick. So that's how you know that those sides correspond. When they ask you to name a polygon, you name a polygon with its vertices. So the name of this quadrilateral is CAMP. Its classification would be a quadrilateral. Okay, so it's actually a convex quadrilateral. So you could go that far. So when they ask you for a name, you need to use the vertices. Just like you have a name, for example, if your name is Markia, that's your name. Your classification may be sophomore, or it may be female. Those are classifications. So that's like quadrilateral or regular quadrilateral, or anything that has to do with its number of sides. But when you name it, you name something with its vertices. That's very important. Okay, we're going to stop 1.4 right there. That's going to be 1.4, and when we pick up, we'll pick up with 1.5 in just a second.